So now we looked at machine learning frameworks. Let's now jump into deep learning frameworks. So as I mentioned, scikit-learn is great for machine learning, but has sort of stopped there. Deep learning requires a lot more specialized equipment, for example, the GPU, using a GPU efficiently, and there's also a lot more parameters. So scikit-learn has sort of said, we're going to focus on the machine learning part. You can implement some neural networks in scikit-learn, but when it comes to heavy-duty deep learning, you usually want to go towards libraries that were built just for deep learning. So this is what we're going to talk about in the next few slides. So first of all, let's start with what makes a good deep learning framework. There's probably a lot of different answers to this question. In my opinion, something that makes a good deep learning framework is, one, it's really easy to implement a neural network. So you, as a user, can just import your library, and if you have some kind of an idea of what kind of model you want to build, there should be very little resistance in building this model. But also, seeing as most of you are probably from industry in this room, it should be easy to deploy. If you're able to get a really good classifier but have no idea how you can possibly send this to production, then this could be actually critical to the problem that you're solving. It could be that you actually need to deploy this and scale this, and you need to know that your framework is able to do this. So a lot of these frameworks are built around the idea of computational graphs. This is a bit more detail that we're not going to go into right now, but the point is that you have these frameworks that really optimize all of your operations. And you can see here, there's this really neat animation of a computational graph. This is from the TensorFlow website. And what it does is it essentially breaks down all the common operations that happen in deep learning, and it really optimizes them for when you're running your code on GPUs. And again, they facilitate operations like backpropagation, gradient descent, all your optimizers, and take care of this for you. So now let's look at the history of deep learning frameworks. So scikit-learn came out in about 2007, and deep learning was already it existed in 2007, but wasn't as big as it is today. So it's really around 2008, we had this really important contribution, which was created at Mila, which was called Theano. And Theano was a pretty important deep learning framework in terms of deep learning research. And it was an open source library, and it was meant to facilitate researchers to just come up with new models and test their ideas quickly. So this was developed by Mila for a very long time. And it's only around 2017 that Mila finally took the decision to stop supporting Theano officially and drop the project. It's not a bad thing necessarily. Since then, there have been a lot of frameworks that have come along, and we're going to talk about some of them. And again, the rationale behind that was Mila had contributed as much as it could, and at this point, some bigger frameworks out there like TensorFlow and PyTorch were backed by industry, just had better resources to support these libraries for the users that they now had. So Mila just decided that it was time to move on to different projects and contribute back to the community in another different, meaningful way. So as you can see, throughout the years since 2008, lots of deep learning frameworks have appeared on the scene. We have libraries like Caffe, MXNet, PyTorch. So we're not going to go through all of them. We're really going to highlight two important ones, which, in my opinion, are kind of mostly used these days. And these two are TensorFlow and PyTorch. So again, let's try a raise of hands. Who's heard of TensorFlow? OK, we still got a good amount of people. How about PyTorch? OK, now let's try something else. Who uses TensorFlow regularly? OK, and who uses PyTorch regularly? OK, not many people. Good. OK, so most of you don't necessarily use either framework. So today's a good day to talk about them and figure out which one might work best for you. And actually, I've been giving this talk now for about a year. And I have to update this slide all the time because things keep on changing. For example, TensorFlow is now officially in RC. It went from beta to RC just a few weeks ago, from alpha to beta another few weeks ago. It keeps on evolving. Even PyTorch, when I first gave this talk, was at 0.4. So the ecosystem is really quickly changing, and a lot of this information might change. But let's talk about framework usage in papers submitted. This is usually a good indicator. So if we look at iClear, the difference in 2018 to 2019 in terms of frameworks used. So we have we're comparing TensorFlow and PyTorch right now. And you can see that TensorFlow has been kind of steady over the years, a lot of researchers using it, but PyTorch is really where we see a big explosion. From 2018 to 2019, we see that there are a lot more people using it, and there's probably a reason for this. I like these tweets from Andrei Karpathy, who is the head AI researcher at Tesla's self-driving cars. So you can kind of see the evolution of his feeling towards different frameworks. So this is in February 2017. He first talks about how MATLAB is so 2012, Caffe 2013, Theano 2014, and then he's very excited about TensorFlow. He says TensorFlow is the new greatest thing. And then you look at his tweet just a few months later, and he's finally given PyTorch a try. And he says, I've been using PyTorch for a few months now, and I've never felt better. I have more energy, my skin is clearer. So you can see how people's reactions to these different frameworks change all the time. And this is just because they evolve based on the users. And because they're open source, everyone can contribute back and improve them in their own ways. So let's compare the two. And again, even this chart has changed a lot when I first started giving this talk. There used to be a lot of noticeable differences between the two. And now you're going to see that the charts have more or less aligned. And there's probably a reason for this. PyTorch learns from TensorFlow just like TensorFlow learns from PyTorch. They're both open source projects, and people in general tend to like the same things. So let's go through a list of differences. First of all, PyTorch is, well, they're both open source. PyTorch uses the BSD license, whereas TensorFlow uses the Apache license. Little details there. PyTorch is backed by Facebook. That's an important detail. So they have a lot of their funding that comes from Facebook, whereas TensorFlow is backed by Google. So remember how I was saying that Mila stopped contributing to Theano? It's because when you're comparing the resources that Facebook and Google have to throw into these projects compared to Mila, it just made more sense to take a step back and let them do their thing. So a really important thing is GPU support, cuDNN support. So we're going to go through what GPUs and TPUs are later. They're hardware that allow you to accelerate these computations, and they both support them. But again, this wasn't always the case. Visualizations, so they both now have the same visualization tools available, even though that wasn't always the case. But TensorBoard, a really cool tool. We're going to go through it a bit later on for visualizing your experiments as they go on with time. This is probably the most important point in my opinion, whether they're Pythonic or not. PyTorch was developed as a Python-first language. So when PyTorch was released, the idea was always you're writing Python code. There's no ambiguity there. TensorFlow, for those of you who have used TensorFlow in its earlier days, it was really hard to get started. And there's reasons for that, again, for optimizations. But the debugging was a lot harder. It wasn't like your typical debugging in Python. So that, in my opinion, was one of the main points that I would raise. But again, since TensorFlow 2.0, this has changed a lot. They've learned a lot from PyTorch. They've learned a lot of what people liked about debugging. And now eager mode is default in TensorFlow 2.0, which means that, again, you can set breakpoints a lot easier in your code. Production ready, so again, for industry, very important. Can you go from an idea to code in production and deploy it to your users relatively seamlessly and not lose anything in performance? TensorFlow, I would say, is probably better suited for that, for a few reasons, but mainly because they've been around longer. They're battle tested, they have a lot more tools available. You have tools like TensorFlow.js, which allow you to code TensorFlow directly in the browser, so you can do neural network calculations natively on your user's browser. You have things like TensorFlow Lite, TF serving, which allow you to set up APIs pretty seamlessly, and these are some really powerful tools. PyTorch, again, this is kind of what Facebook is using internally. They used to use Caffe and have switched over to PyTorch. So they're also production ready. They have this torch just-in-time script that you can use to convert from a dynamic to a static graph. We'll go through that a bit later. But the point is you have this thing called torch script, which does allow you to go into production. But again, this is still relatively new. It's come out in the last year or so. So not necessarily battle-tested per se, but definitely going in the right direction. They both have their own sets of pre-trained models, so both PyTorch Hub and TensorFlow Hub. So you can go in there and just directly from your Python code download some pre-trained models that are pretty well-known, that you might want to use all the time. So models like VGG, MNIST, even I think they're starting to do transformers now. So you can go ahead and download these models relatively easily, and they're already pre-trained, which is really neat because sometimes training these models can take a long time and a lot of resources. And finally, biggest difference, I would say, between the two is the difference in the computational graph. So PyTorch was from the start built as a dynamic computational graph, whereas TensorFlow was built as a static computational graph. And the big difference here is how this graph of computations, the graph that we saw earlier with the fancy animations, how this graph is built. And originally, TensorFlow was built such that you had to build the entire graph before you can run your code. Whereas PyTorch was built so that this graph would be built as your code was running. And the big difference is that you can imagine if your graph is building as your code is running, you can make mistakes and your graph will still, or your code will still run up until that mistake. And it becomes really easy to diagnose that mistake. Whereas if your graph has to be compiled from the start, which was how TensorFlow was originally designed, then it can be a lot harder to find where your mistakes are because you have to build the entire graph first and then try to run things through it. So it's a lot harder to debug. The reason why you would have a dynamic versus a static graph is simply performance. Originally, TensorFlow was built around performance, and definitely the static graph is more performant than the dynamic graph. But again, users preferred the dynamic graph, and that's why, in my opinion, it's probably a lot more popular in the research community to be using PyTorch. And in fact, throughout the tutorials today and throughout the tutorials this week, we'll be using PyTorch. So we have PyTorch, we have TensorFlow, but what's really neat as well is we have these wrapper APIs that are available. So you can essentially think of these as libraries on top of libraries that allow you to make abstractions. Abstractions because it just makes these libraries a lot more user-friendly. And more often than not, you'll find yourselves, as you become more and more involved in deep learning, doing some tasks over and over. And these tasks can involve writing trading loops, writing evaluation scripts, and a lot of these are very similar from experiment to experiment, but from context to context. And it can be easy to make mistakes in these. So you'll have libraries like Keras and libraries like PyTorch Lightning, which I linked to in this slide as well, that allow you to wrap around these libraries and to just make training relatively simple models a lot easier and a lot more like scikit-learn, where you just call a .fit kind of method and everything magically happens.